Welcome to this presentation on causality and selection. I'd like to start with some food for thought. After your studies, you join a large Dutch health insurer. The problem the firm faces is that people are not used to evidence-based decision making. The insurer wants to change this, which is why you have been hired. Over the last years, the IT department has upgraded the data infrastructure that contains all health records for their clients and information on the packages people choose. All these data are now available for analysis, but nobody really knows what to do with them. Your boss has a medical background and has run clinical trials in the past. He intuits that one cannot simply look at the data, but that one needs to do this in a systematic way. That's why he asks you to give a 30-minute presentation on the topic correlation is not causation, and to formally define causal effects. He wants you to base this presentation on what you have learned at university, but he asks you to explain things in an intuitive way. I'd like to start with this because I think it nicely describes what's going on at firms these days, and it alludes to this statement that correlation is not causation that many of us have heard, but that not so many of us have probably thought about more in terms of formalizing it in any way. And what I want to do here in this presentation is to do exactly that, and that will provide us with a very useful base we can start from in order to think about causal effects and how to estimate them. All right, so let's first think about predictions. Clearly, predictions are important in practice. You see this by basically just opening your eyes and ears. You see them all over the place, and you hear about them all over the place. Why are they important? Well, once I can predict something, then I can prepare for it and react. And many of the tools in computer science are made, constructed in a way so that we can make the best possible predictions. What are examples? The weather, right? So if I know that tomorrow it's going to be bad weather, or today, later today, then I can prepare by wearing the right clothes, by taking an umbrella, for instance, by choosing a different way of traveling. Other things one can predict, and then one often sees predicted, is GDP, gross domestic product, so what is being produced in an economy, or GDP growth. The unemployment rate is another example. Then the likelihood that a customer defaults on a loan and what the loss given default is. So that's a prediction that's important when we want to evaluate how much risk a bank is bearing. One can predict sales for firms. That's important when it comes to thinking about how many people to hire for next year. And one can make predictions related to global warming, right? So one can predict by how much temperatures will rise over the next 10 years. And obviously for all this, we'll use data. Now, what are causal effects? Causal effects are effects of possible interventions. At least that's one way to think about them. What are examples? So examples would be the effect of labor market policy on unemployment, education on wages, the death penalty on crime rates, advertising and prices on sales, CEO compensation on stock performance, stimulus package on growth, or the effect of emissions reductions on global warming. So let's look at this very last example. So a prediction would be how much would global warming be? And here a causal effect is how much will global warming be when I do this thing or when I do that thing, right? So by how much do I change global warming or the evolution of global warming when I adopt a particular policy? And by just looking at these examples, you see that in many situations, knowing about causal effects is actually what we want. So we want to go beyond predicting something. We want to learn about causal effects because causal effects are very closely related to decisions we take. So they inform decisions we do take, and in that sense, they're related to evidence-based policymaking. Let's look at an example. So let's think about the effect of hospital use on health, and by hospital use, I mean here receiving some treatment. So suppose you look at data, then these data show a negative correlation between receiving a treatment and health. And here again, this should be some sort of an elective treatment. I'm thinking about getting that treatment, and I want to know what the effect of that on health is because it's not obvious. But yeah, so I look at data, I see this negative correlation, and that negative correlation, what does it mean? So I can first of all translate it into predictions or into the predictions context. So when I have a negative correlation between visiting a hospital and health, then it means that we predict health to be worse when we know that somebody visited a hospital. And at the same time, we predict that someone is more likely to visit a hospital when they're in bad health. All right, so this is already quite convoluted. So it's not all that clear how that is related to what I'm actually interested in, which is the effect of hospital use on health. And that is precisely that third bullet point here again, causation is not correlation. Now, what is the issue? The issue is that hospital visitors are not a random group from the population. Hospital visitors are a selected group. What that means in turn is that when I look at health for those who didn't visit a hospital, then that's not very useful. When I want to think about the health of hospital users or visitors, for the hypothetical situation in which they hadn't visited a hospital. And this is sometimes called the counterfactual. Okay? So I just want to point out before moving on that we've already touched upon certain things that will be more clearly defined: selected group or selection, and counterfactual. Now I can also do this using real data. So I've some numbers here actually that come from the German socioeconomic panel. And the information in that data set is on whether there was at least one hospital visit and health status. So these are both indicator variables, so 0, 1. One is called HOSP and the other one is called good H. And one when somebody visited a hospital and one when somebody is in good health. So I'm regressing good health on hospital, and what I'm going to get is estimates, obviously. There's a constant term. My estimate is going to be 0.545 with a standard error of 0.003. And the coefficient on hospital is minus 0.254 with a standard error of 0.009. Okay, now I've not calculated averages, but I've run a regression. So let's translate this into conditional expectations. So what is the expectation of good health if somebody does not go to hospital? It will be the constant term. So it's 0.545, which means that among all people who do not go to hospital, the fraction of people who is in good health is 54.5%. Now, second question, what is the expectation of good health given that I do go to the hospital? It's gonna be this 0.545 plus the coefficient on HOSP, so plus minus 0.254, so that's going to be around 0.3. So that means that among all people who visit a hospital, 30% are going to be in good health. Finally, what's the interpretation of the coefficient on HOSP? Well, the interpretation is that it is the difference in the conditional expectation of being in good health, that indicator for being in good health, between those who do go to hospital and those who don't, right? So it changes that likelihood that somebody is in good health by 25.4 percentage points. Let's take this as a starting point, or as a motivation, if you like, to formalize causality. First of all, or to start, let's denote by DI whether unit I or individual I, these are always going to be the same thing for me, so I'm going to use the words interchangeably. So let's denote by DI whether somebody received a treatment. Okay? And a treatment is either yes or no. And, DI is equal to 1 if unit I is treated, and DI is equal to 0 if unit I is not treated. Next to that, I have two potential outcomes. These potential outcomes are Y1I and Y0I. Y1I is the outcome when somebody is treated, and Y0I is the outcome when somebody is not treated. And by somebody, I mean here person I. Okay, so for each person, I have two outcomes, one if treated and one if not treated. Now the thing is, of course, in my data, I'm only going to observe one of them, right? I'm going to observe Y1I if somebody is treated, and I'm going to observe Y0I if somebody is not treated. And I can write these two bullet points here together as yi is di y1i plus 1 minus di y0i. So yi is my observed outcome. If di is equal to 1, then I'm going to have 1 times y1i plus 1 minus 1, which is 0 times y0i. If di is equal to 0, I'm going to have 0 times y1i plus 1 minus 0 times y0i. So I'm basically just representing these two bullet points here in one equation. What is now the treatment effect? For unit I, the effect of being treated is the difference between the two potential outcomes, and that difference is here denoted by delta I. And what you see here is that this definition is actually at the unit level. Okay, so and I have a little subscript I here, causal effects can be heterogeneous, and that means they can differ across units I. One more thing about the potential outcomes model. Sometimes this is also called the counterfactual framework. Now I have a definition of a causal effect at the individual level, and in the best of cases, I'm just going to be able to estimate causal effects at the individual level. And then what I can do is I can simply report summary statistics of that, right? So I will be able to draw a histogram, for instance, or draw a histogram for certain groups in the population. But in general, that's not possible. And we're going to see that at best we can estimate some average of a causal effect. So the most obvious average one can think about is the average treatment effect. The average treatment effect describes how much, on average, a unit in the population benefits from the treatment. So it's the formally the expectation of the individual treatment effect. And the expectation is taken across individuals. And that's going to be the expectation of the difference in the two potential outcomes, as we've seen before, as we've defined before. And that's an expectation of a difference, and that will be the difference in the expectation of the two between the two potential outcomes. Okay. So what that means is we compare the expected potential outcome when treated here with the expected potential outcome when not treated there. And notice that actually the literature is a little bit sloppy here, as it uses the terms average and expectation interchangeably. And in a separate presentation entitled Econometrics for Data Scientists, I talk a little bit about this. I talk about the details on the difference between the two. So the average is an estimator of the expectation. So one is a population quantity, that would be the expectation, and the other one is an estimator of that population quantity. Another average treatment effect is the average treatment effect on the treated. That one is often abbreviated by ATT. It describes how much, on average, those individuals who receive the treatment benefit from it, or by how much the outcome changes due to the treatment on average for them. The average treatment effect on the treated is defined as the expectation of the treatment effect conditional on being treated. So again, that will be the expectation of the difference in the between the two potential outcomes conditional on being treated. And that is again the difference in expectations between the expectation of y1i given di is equal to 1 and the expectation of y not I given that d is equal to 1. One interesting thing here is that we actually observe the expectation of y1i given di is equal to 1, because when di is equal to 1, then y1i is by construction going to be equal to yi. So I've also written it down here because this is simply the observed outcome in expectation or on average among those who have been treated. However, the expectation of y not I conditional on di is equal to 1 is counterfactual and therefore unobserved. Okay, so when di is equal to 1, then I'm never going to observe y not I. I'm only going to observe y1i. And yeah, that's a challenge. Now, back to our example, the effect of hospital use on health. So the average treatment effect, which is by the way, often abbreviated by ATE, answers the question, if we assign all people to hospitals and give them all the treatment, how would the health of people change on average if they had not been assigned to it before? Okay, that's nonsensical, right? And you see this already in this context here, so that's why I like this example actually. Many people would never even consider choosing to receive that treatment, right? And for them, the treatment effect is 0 at best. It might be negative actually. The average treatment effect on the treated, however, is a much more interesting quantity to look at. It asks the question, on average, how did the health of people who went to the hospital and received that treatment actually change? Okay, so that's a sensible thing to ask, because in some sense it quantifies the benefit of the treatment on average across people who received it. So we can do a cost-benefit analysis. So we can compare this to the average cost. Only in special cases, the answer to both questions is the same. In general, if treatment effects don't vary too much across people, in general, it really matters what kind of decision one wants to take, what one is interested in for the particular average one wants to look at. And here in this particular case here, the average treatment effect on the treated seems to be a sensible quantity to look at. Now next, let's talk about selection, which is also an important concept in this context. To talk about selection, let's start from the question why the average treatment effect is actually not the difference of observed outcomes. Okay, so many people would say, intuitively, I just look at the average outcome for those who received the treatment, which actually is this quantity here, and I look at the average outcome for those who didn't receive the treatment, and I take the difference between these two. So the question here I'm asking is what is that difference? Can we say something about that difference? Can we say something more than this difference is not informative? So keep in mind when we discuss this here that what people have in the backs of their minds when they do this is that somehow treatment choice is or treatment assignment is random. But in practice, in general, whether or not somebody receives the treatment is a choice that is quite deliberate. And that choice is often made in light of the effect of that choice on the outcome. And if that is the case, then we actually say that people self-select into the treatment or are selected into the treatment when somebody assigns them to the treatment based on that. Okay? Just think about it in terms of, somebody says, hey, the effect of the treatment will be really, really good for you, so therefore you should take it, and this then makes people take the treatment. Okay, so if we have a situation like this, then people are not randomly assigned to the treatment. Now, keeping this in mind, let's go back to this question, what this observed difference in the outcomes between the two groups is on average, or the average, the observed difference in the average between the two groups actually is. And with our framework, we can now actually write down what that difference is. So let's do that. So I'm again putting here on the left-hand side the expectation of the outcome for the treated minus the expectation of the outcome for the untreated. So the expectation of yi given di is equal to 1 is equal to the expectation of y1i given di is equal to 1. So let's put that here. So that's going to be the first term on the right hand side, the expectation of y1i given di is equal to 1. Minus the expectation of yi given di is equal to 0. So when di is equal to 0, then yi is always equal to y not I. Let's put that here, last term. Okay, and I'm just going to add actually two terms here to these two. So the first one and the last one. I'm just going to subtract first the expectation of y not I given di is equal to 1, and then I'm just going to add it again, the expectation of y not I given di is equal to 1. I can always do that because these two together are equal to 0. So, but if I do that, if I write this difference between two terms as the sum of two differences by simply adding and subtracting this term here, then I can see that the observed difference, the average outcome, is actually equal to the average treatment effect on the treated plus some extra term, and this is going to be selection bias. So in a way, I'm defining selection bias in this particular way. Okay, let's verify that quickly. So this one here is the average treatment effect on the treated. I said the expectation of y1i given di is equal to 1 minus the expectation of y not I given di is equal to 1. Indeed, this is the average treatment effect on the treated. So next, let's look at selection bias. So what is selection bias? Selection bias here, when I write it out like this, is the expectation in the baseline outcome in y not I given di is equal to 1 minus the expectation in y not I given di is equal to 0. Okay? So what that means in the health example is, if I say that nobody gets the treatment, right? Not even the ones who actually got it, and I just think about the outcome, then I get that without the treatment, those who later get it are different on average in terms of the outcome than those who do not get it. Okay, and most likely these are the ones who will be in worse health. Okay. Finally, again, what do we observe? We observe the expectation of y1i given di is equal to 1 and the expectation of y not I given di is equal to 0, but I'm not going to observe the expectation of y not I given di is equal to 1. Okay, so I'm observing this quantity here. I'm not observing this quantity here. I'm not observing this quantity here because it's the same, and I'm again observing this quantity here. I can also put this into a nice table. So what this table shows is in the rows, treatment status, whether somebody is treated or not. Treated here, 1, not treated, 0. Then I have the two potential outcomes, y not I and y1i. And then I have two colors, okay? If di is equal to 0, then I actually observe y not I. So I basically observe the expectation of y not I given di is equal to 0. When di is equal to 1, then I observe the expectation of y1i given di is equal to 1. So I observe the diagonal elements here. What I do not observe are the off-diagonal elements, the quantities in blue. So the expectation of y1i given di is equal to 0, and the expectation of y not I given di is equal to 1. So in words, I do not observe what would have happened to those who were not treated had they gotten the treatment. There's this first blue quantity here. And I also don't observe what would have happened to those who did get the treatment had they not been treated. Okay? I only observe the diagonal elements. Now let's condition on di is equal to 1 and look at the difference between the two columns. This is the average treatment effect on the treated, which I denoted by ATT. It's the expectation of y1i given di is equal to 1 minus the expectation of y naught I given di is equal to 1 again. There's another average treatment effect that I didn't talk about really, which is the average treatment effect on the controls or the not treated. So that would simply be the difference between these two quantities here. So when I compare across columns, then I always get an average treatment effect in this table. When I compare across the two rows for y naught I, then I get selection bias 1. This is the selection bias I just talked about. It's the difference in the expected y naught I between the treated and the untreated. This is my selection bias. I can also, define selection bias as the difference in the two y1s, but I don't want to talk about that more because usually that's not done. So the usual way to do that is to define it like this. But sometimes it might be useful to also look at selection bias 2. Now again, let's look at an example. Here's again a table. Here's the same table. And I've now filled in the numbers that we have already seen when I talked about the regression analysis with the German socioeconomic panel data. And what we talked about were 3 numbers. We talked about 0.55, 0.3, and the difference between the two. Okay, so the difference between the two was minus 0.25. Okay, so we talked about this black number and that black number and the difference between these two black numbers. What I've now printed here is a table that also just makes up 2 additional numbers, the 2 blue numbers. And there's no way we could have learned about these 2 numbers from the data that I had used for this regression. These 2 blue numbers are simply made up, and they're simply made up for illustration purposes here. Okay. So an exercise now could be to calculate the following quantities using this table, and the quantities are the expected y naught I, the expected y1 I, the average treatment effect, the average treatment effect on the treated, and selection bias as we talked about it. So the difference in the y naught I between the 2 groups. And what one does need for that is one additional quantity, and that is the probability that somebody received the treatment, and that is 0.12, 12%. Okay, so I'm not going to do this exercise here, but I would like to encourage you to do it yourselves. It's a relatively easy thing to do, but it's quite instructive to do it simply to kind of make sure one really understands all these definitions. And it's quite instructive, so that's why I'm not doing it here. And I leave it to you to do it yourselves. Good. final thing on this slide is that the statement correlation is not causation can also be related to this table. You can think of the correlation as being related to the comparison of these two numbers here on the diagonal, 0.3 and 0.55. Okay, so this is the correlation. So basically, we see the outcome for the treated, but then we see basically the average y1i, and we see the average y0i for the untreated. But the interesting thing is that you see here that the average outcome for the treated is lower than the average outcome for the untreated, the average observed outcome for the untreated. But by comparing across columns, you see that the treatment effect is 0 for the untreated and is 0.1 for the treated. So what that means is that we actually have a negative correlation in the data, whereas actually we have a positive effect on average of the treatment on the treated, but also on average in the population, because that will be an average between these two numbers. Okay, so causation conversely can be thought of as this difference, as these two differences in that last column. So again, correlation is to compare 0.55 with 0.3, and causation is to compare within row across columns. Now we've seen already quite a bit. To summarize this a little bit, let me just tell you what is sometimes called the fundamental problem of causal inference. So our aim is to estimate parameters such as the ATE or the ATT. And the fundamental problem of causal inference is now that in general, we actually do not observe counterfactuals. And therefore, we can't directly estimate the expected y0i or the expected y1i. And we can also not estimate the expected y0i given di is equal to 1, which we would need in order to calculate the average treatment effect on the treated. However, sometimes we can estimate counterfactuals, in some situations, as we will see. The approach is usually to carefully exploit only the exogenous part of the variation in the treatment, and that's a very general statement at this point. That's going to become clear what that means when we actually look at the details. And generally, what we want to avoid is to make use of variation that is related to selection, to the selection term that we have seen before. And sources of such exogenous variation can be experiments, and there are two types of experiments that we're going to distinguish between. These are social experiments and natural experiments. And before I move on, let me point you to a nice read that is a little bit more philosophical, but very much related to the fundamental problem of causal inference. That's a sort of classic article by Holland from 1986, and it's entitled Statistics and Causal Inference in the Journal of the American Statistical Association. Now let's talk about social experiments and natural experiments. A social experiment is designed and implemented consciously by human researchers, and that involves some form of random assignment. So we know this already from clinical trials, for instance, or experiments in psychology. So for clinical trials, when it comes to finding out whether a drug works, one recruits people, and then one randomly assigns them to the treatment group or the control group without telling them. So they all take a pill or some other, get some vaccine or something, and then one basically follows them over time, and one sees what happens over time. In psychology, one would recruit people and give them different treatments, and then one would see how they react to that. There's a distinction between lab experiments and field experiments. So lab experiments would be, somewhere, say, in a room where one lets people do something in a sort of artificial context. Field experiments are experiments that are carried out, in real life, and at the same time, one finds a clever way of randomizing people into one treatment condition or another. In tech companies, this is sometimes now, or usually now, called A/B testing, and there it's done actually a lot, and we normally don't notice, but what is happening there is that one uses like a platform or an app or some website or something, and things are simply shown in a different way, right? Things are arranged differently. The order of search results is, randomly changed, things like that. Okay, so these are all social experiments. Deliberate randomization is taking place here. As opposed to that, there are natural experiments, and here the purpose was not to really conduct an experiment, but in some sense, by chance, there is a random element to what has happened, and one can exploit this randomness in a clever way to estimate causal effects. So there's some source of randomization that is as if there has been some random assignment. Okay, but there was no conscious randomized treatment and control design. So what could that be? Changes in legislation or administrative rules, geographic variation, or thresholds, right? When somebody got treated in some way when that person was born after a certain date, and in some other way if that person was born before that date, and one can convince oneself that it's kind of random whether one has been born just before or just after that date, then that random element is enough to actually estimate causal effects, and we're going to come back to that. All right, so let's now again think about some real-world situation to motivate what is to come. Suppose you've just joined a startup as a data scientist. Your employer offers a web-based product to other businesses that help them to serve their own customers more efficiently. There is no one price. Instead, potential customers fill in a form, and based on the information they provide, they get a price quote. The founder wants to base pricing on systematic empirical evidence and wants to learn about the price sensitivity of potential customers by means of an experiment. You're asked to explain to him how an experiment could be designed to achieve this goal and what can potentially go wrong when designing an experiment. So this is what we should keep in mind when we now look at what comes. So first of all, let's think about random assignment. Okay, let's formalize random assignment, and obviously what I'm going to use here heavily is the potential outcomes framework. Okay, so let's just say that there has been a random assignment. So what does that mean in the potential outcomes framework? So I have these two potential outcomes, y1i and y not I. So for each I have two outcomes. Okay, and I'm gonna write that this is independent of di. Okay, di is treatment status, and this is the symbol for independence. You know this probably from orthogonality or zero correlation. Here I'm just going to use it to denote independence. Okay, so if I now formalize it basically like this, then it means that treatment status is independent of what these things are, right? So before I talked about a selection problem would mean that when the difference between these two y's is particularly big, for instance, then di is going to be more likely equal to 1. So that would be a selection problem that would result from that. Here we have the opposite. So here I've assumed that the potential outcomes are independent of di. So that means that when the difference is particularly big, it's not more likely that di is equal to 1. This is what independence means. It's really you roll the dice. So di is assigned completely independently of the potential outcomes. Why does this help? It helps because it basically solves what we have called before the selection problem, or it solves the selection effect. It basically leads to the following. So when I look at the expectation of y1i, then that will be the expectation. No, I'm sorry. What I want to say is if this is true, then what will be the case is that the expectation of y1i is equal to the expectation of y1i given di is equal to 1. And it's also going to be equal to the expectation of y1i given di is equal to 0. Why is that? Because I've assumed that the y's are independent of the d's. So that means that when I look at this expectation of y1i, it does not matter whether I condition on d is equal to 1 or d is equal to 0, or I don't condition on it at all, because these are independent of one another. Okay, because y1i is independent of di. At the same time, y not I is independent of di, and therefore I have also that the expectation of y not I is the same no matter whether I do not condition on it, or I condition on di is equal to 1, or I condition on di is equal to 0. Okay, so that's going to be helpful. Note that, and this is not completely correct, what I wanted to write here is that the average treatment effect is equal to the average treatment effect on the treated under random assignment. Let me just change that. Here we go. How can I see this? The average treatment effect is going to be the difference between this quantity here and this quantity here. But this quantity here is equal to this quantity here, and this quantity here is equal to this quantity here. So if this difference takes on a particular value, then also that difference is going to take on the exact same value. Okay, and that makes also perfect intuitive sense because those who have been treated are a random selection of people. So therefore, the treatment effect for this random selection of people should be the average treatment effect in the population. Let's also look at this in terms of the table we have seen before. So before I told you that we observe this black quantity and we observe this black quantity. Okay, and that selection bias is basically the difference between these two quantities here. Now, on the random assignment, what I have is, and this is now written with these red equality symbols. This first quantity here is equal to the second quantity, and also here in this second column, this quantity here is equal to this quantity here. Random assignment means that the expectations do not depend on treatment status, right? So the expectation of y not I conditional on di is equal to 0 is equal to the expectation of y not I conditional on di is equal to 1. And this is actually equal to the expectation of y not I unconditionally. Selection bias is the difference between these two. And since the conditioning set doesn't matter anymore, the difference is going to be 0. So what we defined before as a selection bias will be 0 under random assignment. And when you recall that before we said that the observed difference in outcomes is equal to the average treatment effect on the treated plus selection bias, and selection bias is now equal to 0, then it must mean by implication that the observed difference between outcomes is actually then under random assignment equal to the average treatment effect on the treated. And then let's combine that with the other statement I just made, namely that the average treatment effect on the treated is equal to the average treatment effect in the population under random assignment. So that means then that under random assignment, the observed difference in outcomes is equal to the average treatment effect. Great. Just for completeness in some sense, this is sometimes called the difference in means estimator, right? So under random assignment, the expected y1i given di is equal to 1 and the expected y not i given di is equal to 0 can be estimated by the average outcome among the treated and untreated respectively, and this is then meaningful to take the difference between the two, and the resulting estimator for the treatment effect is called the difference in means estimator. So this is a fancy name for simply calculating the average outcome among the treated and subtracting from it the average outcome among the untreated. And I can also do this using a regression and OLS regression, and the advantage of that is that I get also coefficient estimates with standard errors, and I get a statistical test right away. Let's look at this in some more detail. So what I can do is I can specify the regression model like this. So I say yi is beta 1 plus beta 2 di plus ui, and just as a little aside, there's really no unified notation for this in the literature. And here I'm departing from the usual way to write a regression model in say classical econometrics. This here is not classical econometrics. That's the more modern treatment effects part of econometrics. In classical econometrics, one would write this using a lowercase yi, and then one would normally have beta naught plus beta 1 little xi plus, and then an epsilon I instead of the ui. This is also what I've actually used in this other presentation, econometrics for data scientists. But please be a little bit flexible, and that's why I've actually not unified it here either. You see that here I'm simply calling these betas beta 1 and 2 instead of not and 1. I'm calling this di instead of x, and this is uppercase, and this is also uppercase, and the error term is not epsilon I but ui. But in the end of the day, it's the exact same bivariate regression model. Now, let's think about randomized experiments, in the context of this model. It's always true, without any assumptions on randomization, that I can write down a conditional expectation of the outcome conditional on the treatment for this regression model, right? So when I have this regression model, I can always write down the expectation of yi given di. What I do is I substitute in this regression model for yi. So yi is beta 1 plus beta 2 di plus ui. So it's an expectation of a sum that will be the sum of expectations, and I'm going to have constants beta 1 and beta 2. No, actually beta 1, I'm sorry. Beta 1 is a constant term, so there is no expectation really that is playing a role here. But I'm going to think actually of beta 2 as not a constant now for the moment, but I'm going to think about it as a random variable. So I'm going to have the expectation of beta 2 given di is equal to 1 times di. Given di is equal to 1 times di. So it's when di is equal to 0, then this will actually go away. Plus the expectation of ui given di. What does that mean? So this here is written down for a general di, and I should have really put here di is equal to 1. So let me just do that. Here we go. So what that means is that when I now take this equation here, which is for general di, then I can also write it down for specific di's and just take the difference between the two. Okay, so I'm taking this and I'm evaluating this for di is equal to 1. Okay, then again I'm going to have beta 1. I'm going to have the expectation of beta 2 given di is equal to 1 times 1 plus the expectation of ui given that di is equal to 1. So this is exactly what I have written down here. Okay, minus now the expectation of the outcome yi given di is equal to 0. So minus beta 1, this beta 1, plus this one here becomes 0, this second term, because di is going to be equal to 0. Plus the expectation of ui given di is equal to 0, which is this term here. All right, when I now look at this, I see that there's beta 1 here, minus beta 1 here, so that goes away. So what I will have is that this is equal to the expectation of beta 2 given di is equal to 1 plus the difference in the expectation of the ui between di is equal to 1 and di is equal to 0. Okay. Now, for the interpretation, we can actually go back to slide 12. I can just tell you what is on there. This now will come back here. So what we have on the left-hand side here is the difference in the mean outcome between the treated and the untreated, and this is going to be equal to the average treatment effect on the treated which is this, the beta 2 in expectation among the treated, plus selection bias. So what is selection bias? Selection bias is the difference in the expectation of the UI between the treated and the untreated. Okay, in some sense, I've just re-expressed here using a regression framework what we have already seen before. Now, why is this useful? Well, you know from this other presentation, Econometrics for Data Scientists, that the OLS estimator beta 2 hat always estimates exactly this difference in means. So it always estimates this thing here, okay? This is just the result, and I explain it there in detail why that is. And the random assignment, so it always estimates, you know, by implication, this whole stuff here, right? It estimates the sum of the effect of interest and selection bias. Now, under random assignment, what is actually the case is that the error term is independent of the regressor, right? So what that means is that the expected UI given di is equal to 1 is equal to the expected UI given di is equal to 0. But if this is the case, then actually selection bias is equal to 0, and then OLS estimates my parameter of interest, which is the expected beta 2 given di is equal to 1. And again, this is the average treatment effect on the treated. That's kind of cool. This is another way of seeing what OLS actually does and why random assignment does something very helpful here in this context. And random assignment again is the same as what has been called exogeneity before. So when treatment assignment is exogenous, then that's the exact same thing as random assignment here. So in either of the two cases, what I have is that the expected UI given di is equal to 1 is equal to the expected UI given di is equal to 0, and that can also be described as a mean independence of the UI and treatment status. Now, let's look at some examples. Enough methods. Let's look at how this is being used in practice. So in health economics, there has been a big field experiment. There was the so-called RAND health insurance experiment. And what that did was to randomly assign different types of health insurance contracts to people. And here I've just put a reference where you can read about this. So this is a survey article that appeared in the Journal of Economic Perspectives in 2013. It's worth reading, so I can warmly recommend that. Very different context, development economics. Teaching students who lag behind has a positive effect on test scores. So basically giving some people extra help does help. So this is based on, this is about 2 experiments that have been carried out in India. Banerjee and Duflo have just recently gotten the Nobel Prize for work like this. If you want to understand a little bit what one gets a Nobel Prize for in economics, that's worth having a look at, and you are now basically in a position to understand what's going on there. And of course, the real contribution is to do this well and to do this to answer questions that are really relevant in practice. So these are just two things I wanted to mention. Next to that, I would like to talk in a little bit more detail about 4 other examples. So first, from the context of medicine, medical sciences, the effect of beta blockers on mortality, how this is actually assessed using real clinical trials. Then an example from labor economics, so that would be about discrimination in the labor market. Then I want to talk about online experiments. That would be the effect of advertising on sales. And finally, I want to talk about the economics of education, and this is about assigning students to small classes. What this actually does to test scores. And here I put empirical example because I actually have a few numbers that I'd like to share with you for this last example that come straight from regressions I've run. Good. So the effect of beta blockers on mortality is a reference to an article that's not, very recent, but it nicely summarizes actually a whole literature up to that point. Beta blockers have been around for quite a while, so it's also not too crazy to look at an older survey. I'm just going to show you a table, but before that, beta blockers are substances that reduce oxygen demand of the heart through reduction of heart rate and blood pressure. So that's good, when it comes to reducing the death rate in case of heart attacks. But here, the aim was to actually measure this. In general, even though this whole idea of random assignment comes to a large extent from the medical sciences, oftentimes the results are less clear than in other fields, and you see this from this table here. So what do you see? You see basically many different experiments that people have carried out. So each row here is an experiment. So here you see how many people have been allocated a beta blocker, have been allocated a control, and the outcome here is whether people literally die. So 14 out of 56 died, 15 out of 58 died. So you get a percentage of people who died here, and here you get a ratio. If beta blockers really work, then that number here, percentage, should always be smaller than the percentage here, or the ratio should be less than 1. Doesn't really look like it. You can also take the difference that is done here, the variance, and you can do a test, and by and large, what you see here, NS always means not significant. I don't want to talk about this too much longer, but the reason for this is low numbers of cases. Okay, it's not so easy to learn something from random assignment when you have so low numbers, right? So what you see here always is like 100 people or something like this. So that's too little. That's something we can take away, and nowadays also people understand this much better, so they actually design clinical trials ideally with more people. But then again, when it comes to approving, for instance, vaccines, there are multiple phases, and in the beginning, you also have numbers like this. So what you see here is that actually you can't learn all that much from it in a statistical testing sense, at least. Good. Second example is discrimination in the labor market. So simply to give you an idea how you can run an experiment to learn something about this. So you have put a reference up there. So and what these authors have done is to see whether there is employer discrimination, right? The starting point is racial inequality in the US labor market. So blacks are twice as often unemployed as whites, and they earn 20% less. So the question is it that employers discriminate? And the experiment is to send fake applications to employers, and then to see how many people are basically invited for an interview. And what is randomly assigned or manipulated is the perception of race. So race is in the US not put on a CV, but of course people can make up their mind, and what they have done here is to vary the names, and when you give somebody a name that sounds more black, then people are going to think of that applicant as black, and then the question is, is the callback rate lower in the sense that these people get less invitations for an interview. This is how the results look like. And what you see here is already much bigger numbers, right? So I just want to focus here on this first row, all sent applications. So here you have it split up by city, gender, females, males, and then females split up once more. So let's just focus on the top row here. In brackets here, you see always the number of applications they've sent. So much higher numbers, 2,400. White names, African American names, and what you see here is the callback rate. Okay, so these are the fractions of individuals who have been invited for an interview. So 9.65%. 9.65% versus 6.45%, a ratio of 1.5. And then you can actually do a statistical test, and you find a p-value of basically 0, right? So you reject the null of equality. So consequently, you can say that indeed the callback rate for whites is actually higher, significantly higher. Next example is the effect of advertising on sales. That's traditionally really something that people say is hard to measure, but nowadays we of course have other possibilities. Let's put it like this. What's nice about this study here is that it involved randomization, and it took place in an online environment. So what the authors do is to study the effects of online display advertising on both online and in-store purchases. So online display advertising is a bit of an ancient form of advertising. Think of banners and stuff, right? So this was much more prevalent in the early days of the internet. So nowadays we have more targeted advertising in the context of Facebook and Instagram and so on, and also search advertising, right? So sponsored search. Nonetheless, Randomized field experiment, 3 million Yahoo. You might now wonder, what is Yahoo? Yahoo is a search engine that existed in the early days. So they tried to actually sort of catalog the internet. So that was Yahoo. So 3 million Yahoo users who are also past customers of that retailer. So they found a clever way of following them also offline. And what they do is they find significant evidence that ads increase sales by 3.6% for those who have been reached by ads. Okay, so just a little aside before I get there. So there's another article by Lewis and Rao that I put up down here, and they actually explore a little bit more why it's actually not so easy to measure advertising effects, even when one has a large number of observations. Okay, so if you're interested, that might be a nice read for you. So you have put the Yahoo logo. Not many of you might recognize it, but you know, this was big in the early days. What do we see? We basically see the results represented in this table here. And what you see in this table is, you see a dollar sign, right? So, you know, there was a half treatment. It was basically the half of the number of ads. There's a constant term that gives baseline sales, and then full treatment is the full treatment effect, and you get numbers like this, okay? And they translate it in percentage terms, and they come up with these 3 something-ish percent. So you see here that you know, you need enough ads. You need to reach people enough times, a few times, so that you find effects. And you see here stars, so that means that the effect is actually also significantly different from 0. I want to, for now, leave it at that. So go and look at the paper in case you're more interested. What I want you to take away from this is that you know, what we talked about before is happening in practice. So people run these experiments. This costs quite a bit of money to do, because you would you know, randomly assign ads to people, and you would normally not show ads to certain people, but you nevertheless do in order to learn about the effects. What you then get for that investment is you get good estimates, right? As you see basically what the average treatment effect of an ad is. So why would you normally not do that? Normally you would target, right? And you would go for certain groups of people. Here you are targeting, you know, everybody in some sense. So here you're really actually getting at the average treatment effect. Good. Next example is assigning students to small classes. And that is what has been called Project STAR, stands for Student Teacher Achievement Ratio. This was about basically assigning over 7,000 students in 79 schools randomly, at least randomly within school, into one of 3 treatment conditions: small class, regular class, and regular class with aid, so that there was an extra teacher in the class, and then following people for 4 years. These are the first 4 years of school, basically. Teachers were also randomly assigned to classes, yeah, all this started basically in first grade, which is called kindergarten in the US, and then continued through 3rd grade. So it's 0, 1, 2, 3, so it's 4 years for that reason. And the outcome I'm looking at here is test scores. The difference in outcomes across treatment conditions, and again, this is the test score. This here is, by the way, Stata output. Stata is software that is the most common statistical software actually used among economists. It's very much tailored to that purpose. So I've used it to run this analysis here. So what you see here is mean average test scores for the three treatment conditions: small class, regular class, and regular plus 8. So what you see already from this is that small class really had 10% better test score. We can also run a regression here. So basically test score on now true treatment indicators, one for small class and one for regular class with 8. So that means the baseline outcome is regular class without 8. So you see here the 50.55611, that's the baseline outcome. And then in a small class, the outcome is better by 4.27, and in a regular class with 8, it's a little bit worse, but what you see here, here's the t-stat, here's the p-value, here's the standard error, so you see that this effect is not statistically significant. Now, the first thing that can go wrong with experiments is imperfect randomization. This is also sometimes called experimental bias and can be conscious or unconscious. So for instance, the treatment group for a job training program is filled with motivated job searchers and not a random sample of job searchers. It's always a good idea to at least try and test for such failures to randomize. So for Project STAR, one cannot directly compare pre-treatment outcomes, test scores, because we don't have them. So what Krüger, who has written a paper on this data set here, does is to compare pre-treatment characteristics of children, and that would be eligibility for free lunch, age and race. So free lunch is an indicator for basically being socially disadvantaged, and you can basically see here in this table down here how it looks. So non-free lunch or free lunch, and you can see that in small classes, slightly more people are eligible for free lunch than in regular classes, and the most are eligible for free lunch in regular plus 8 classes. So yeah, the question is then, of course, is this like a big effect or not? I don't want to go into details, but you get the flavor, right? You see what we could do. What I actually like much better is a second example I'll get to in a moment, where we can also look at this. Before I get there, let me name the second problem that one could potentially have with experiments. That could be a failure to follow the treatment protocol. So that is called attrition, and would mean that some subjects drop out, for instance, because wealthy parents move children from large classes to private school. Right, so they see that others are in a small class. They don't like that. They think a small class is great, but they don't get it in a public school. So they then take them out and put them to private school. So we lose them in our data, right? And then this is called selective attrition. So certain people are more likely to leave, and that depends on the treatment condition. Okay, and here one could imagine that this happens more often in the control group, when the control group is obviously looking, like a worse treatment in some sense. Another failure to follow the treatment protocol is called imperfect compliance. So it means that some who were assigned the treatment decided not to get it. And that is actually a big thing in practice, because in practice you can't force people to do stuff most of the time. So you can only offer somebody to take a treatment. And some people take the offer and other people don't, right? But you don't have this situation that you can really assign people to a treatment. And this then leads to what is called imperfect compliance. So again, before we talked about the failure to randomize, and then now here we have selective attrition and imperfect compliance. And this brings me back to this paper I had earlier about advertising effects, right? So what they have in this paper is this table here, table 1. And what you see here is 3 columns, right? Full, half, and control. So control group didn't see any of the ads of that retailer. Full did see a lot of ads, and half they saw half basically. Half ads from that retailer and half ads from some half control ads, right? So what you see here first is sample size, massive, right? Very typical for, say, tech companies. Nowadays they even have more, right? So actually like 1 million, right? Then you see characteristics, right? So here female, very nicely sort of balanced between the 3 groups. So randomization was really successful, it seems. Same for age, looks very similar. Yahoo page views, that's a measure of activity. Also actually very much comparable. A little bit more of a difference between those, but then a statistical test, p-value here, 0.132. Not significantly different from 0, the differences, so we shouldn't worry about this too much. Then pre-treatment sales, 2 years and 2 weeks. Also here, all these are not statistically different across groups. Here you see the numbers for pre-treatment sales, 2 years and 2 weeks. Okay, you do see that they show very nice evidence supporting randomization, basically. And then as for selective attrition, that was the problem that, treated or control units would be more likely to leave. So we would sort of lose them over time. And in the context of this experiment here, that would be picked up by the page views, right? So the ones during the period in which they actually saw ads. So how many ads did they see? So we see here that they saw like 3.4 ads on average, 33.66, so no difference, right? So that's supportive evidence of not selectively losing people. All right. So here you see, down here you see, by the way, retailer ad views. So this is the treatment condition. So you see 33.4 ads from that retailer. The half condition you see 16, and the control group doesn't see any of that retailer. Okay. And then here you see the outcomes, basically. Or some other outcomes, not sales, but the click-through rate. So that would be how often people actually clicked on that ad from the retailer, so about 20% of the time. Okay, so yeah, you can do something to provide supportive evidence of randomization, and you can actually also look at the data to find out whether you had selective attrition, and this is actually experiments are carried out all the time by tech companies, and doing all these things is rather standard, but for you, learning about them is very useful. Good. So before we move on, let's pause and then look at some more food for thought. So what can we now do if we have this other problem, which would be imperfect compliance, right? And then let's now just think about this in a different context yet. So you're working now at the employment agency that is paying out unemployment benefits. Your task is to find out what the effect of a training program is on unemployed individuals looking for a job. 2 years ago, the treatment has been offered to a random sample of unemployed individuals, but not all unemployed individuals have decided to participate. How can you now use the data you have on them, on whether they are employed again and how much they earn, to find out what the effect of the program was? So what is going on here is that people have been offered to participate in a program, and some took the offer and some didn't. And whether you got the offer was random. But yeah, it all seems a little bit more complicated. And yeah, our good old friend instrumental variables estimation actually helps us quite a bit in such a situation, it turns out, because we have some randomization we can use. Okay, and in particular, what we can do is we can use randomized treatment assignment as the instrument. It does influence the treatment decision, which is the right-hand side variable whose effect we want to estimate. And at the same time, randomization means it's not related to the error term. So it will actually help us quite a bit to estimate the causal effect of the program on these outcomes, so wages and the likelihood to be employed. Now, to build a bridge and to go beyond, to build a bridge to what we have seen before, and to go beyond what you already know about instrumental variables estimation, let me point out that instrumental variables estimation is also very meaningful in the context of heterogeneous treatment effects. In the 90s, since the 90s, great progress has been made understanding what instrumental variables estimation actually does in that context. So let me give you the gist of it. So suppose the effect of the treatment varies across individuals. This is exactly what we had, right? So before I wrote down this regression equation, beta 1 plus beta 2 times treatment, and I thought of this beta 2 as essentially my individual treatment effect, right? I had the expectation of beta 2 conditional on DI. Now, what does the IV procedure do? So the instrument moves the treatment decision of some individuals, right? So when I go from not being offered the treatment to being offered the treatment, then what is happening is that some people actually go for it and others don't. It moves the treatment decision of some individuals, and these are called compliers. They comply with the treatment assignment. So I said, all this is interesting in the context of imperfect compliance, but those who do take the treatment, these are the compliers. What Invens and Angrist in '94 show is that in such a situation, under additional assumptions that I'm not going to even get into here, what we can do is we can interpret the instrumental variables estimate as an average treatment effect, but yet a different average treatment effect. So it will be the average treatment effect of the average effect of the treatment for the subpopulation of compliers, for those who are motivated to take the treatment essentially by being offered the treatment. So for those who actually then take it. And that is also intuitive. When we are in such a situation, there's basically no hope to learn about the effect the treatment has or would have had for those who never took it, right? Because there's no information related to that in our data. Good. So that brings me to the third and last problem that we might face when we carry out experiments. And obviously there are many more in practice, but these are important ones that I wanted to mention here. And that would be so-called experimental effects that one should always be aware of. That could be that the treatment is associated with extra effort or extra care, right? So one does not only put people into a condition, but at the same time somehow treats them differently, or somehow motivates them to provide more effort, which has nothing to do with the treatment condition itself. So one has to be very careful, and this is actually the reason also why there is a placebo in clinical trials. So people also get a pill when they actually do not get any drug. All right, the pill is just not doing anything. And related to that, it could be, but yet different. It could be that people know that they are in some experiment and therefore behave differently, and that is called the Hawthorne effect. Why is it called that way? The term was coined in '58, actually, when somebody was analyzing early experiments from the 20s at the Hawthorne Works, and that's just like a plant. And what they had done is they had commissioned a study to see if workers would become more productive in higher or lower levels of light. Okay. This was a different design. It was more like, they varied the light over time. So it was what is sometimes called a before-after design. So you didn't have like a treatment and a control group, but nevertheless, the problem is described in situations with a treatment and control group as well. By this Hawthorne effect terminology. Using this terminology, and what happened was that the workers' productivity seemed to improve when changes were made and slumped when the study ended. But in the end of the day, it was not the light that changed productivity. It was simply the fact that workers noticed that something was different and that they were being watched, right? And something was measured. And this is actually something that happens quite a bit in practice, that when people know that something is measured, they behave differently. So what one has to do is one has to make sure at the minimum that the treatment and the control group is affected in the same way by this, right? So basically then both will behave a little bit differently because they're being watched. However, one is only interested in a difference between the two, and that will hopefully cancel out. That is how people think about it most of the time. Good. So to finish, what are the key concepts we have talked about? So this is a little bit of a review. We've talked about potential outcomes. We have talked about treatment effects, how we can define them. We've talked about average treatment effects, the average treatment effect on the treated. We've talked about the fundamental problem of causal inference. We've talked more formally about the difference between correlation and causation. We've talked about selection, self-selection, the selection problem. We have talked about ways of overcoming the selection problem. These would be randomization, social and natural experiments. We have talked about this fancy terminology, difference in means estimator. We have talked about how one can run regressions to basically calculate the same thing. We've talked about imperfect compliance and instrumental variables estimation. We have talked about other potential problems with experiments, and we have talked about ways, or we have talked about the testing for randomization, basically, or providing supportive evidence that there were no problems with randomization. And on the way, we've talked about many other things. I hope you found this presentation useful, and with this, all the best.